Section 3.3, Newton's second law of motion. If the net force acting on an object is not zero, then the object must be accelerating. Here we have a graph, and the y-axis of this graph shows force measured in newtons, and the x-axis shows acceleration, measured in meters per second squared. And we can see there is a straight line relationship. It's called a linear relationship between the force and the acceleration. So for a fixed mass, the greater the force, the larger the acceleration. Similarly, the smaller the force, the smaller the acceleration. We can express this by saying that the acceleration is directly proportional to the net force for a constant mass. And we can write that relationship in this proportionality statement, which states acceleration, and this Greek letter alpha means proportional to. So acceleration is proportional to the net force. Now we can take a different graph, this one showing acceleration on the y-axis and mass in kilograms on the x-axis. And we can see this unique relationship. When you see this relationship, this type of graph, if you've studied math before, you know that this is called an inverse relationship. And what it means is, when the acceleration is high, the mass is low, and when the mass is high, the acceleration is low. So again, when the mass is small, acceleration is high, and when the mass is large, acceleration is low. So they found this by applying a steady force to a bunch of objects of different masses, and they noticed that the smaller the mass, the larger the acceleration, and the larger the mass, the smaller the acceleration. So they summarized this with the proportionality statement stating acceleration is inversely proportional to the mass. And that's why we have 1 over m. That means inversely to the mass. You can combine these two proportionality statements together, stating that acceleration is directly proportional to the net force and inversely proportional to the mass. And this leads to a mathematical relationship, an equation for the net force. You can replace that proportionality constant, or that proportionality symbol, with the equal sign, and we have acceleration is equal to net force over mass. Or if we rearrange it in its most common form, we get this equation here, which states that the net force is equal to the mass times acceleration. This equation is the most important equation for studying Newton's second law. And it's also quietly a summary of Newton's second law, and I'll explain that when we actually express Newton's second law. So net force is the unbalanced or resultant or total force measured in newtons, m is the mass measured in kilograms, and a is the acceleration in meters per second squared. So these studies led to Newton's second law of motion. And Newton's second law of motion states, if the net external force acting on an object is not zero, then the object will accelerate in the direction of this net force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. So this statement right here, the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass, is the basis for that equation we just studied above and a summary of Newton's second law. So this equation that we know is basically a summary for Newton's second law. Let's test it out. Let's see if we can do some problem solving involving Newton's second law of motion. Sample problem number 1. A net force of 36 newtons forward is applied to a volleyball of mass 0.24 kilograms. Determine the acceleration of the volleyball. So we have a volleyball, and there's a net force acting on this volleyball, and it's 36 newtons forward. The mass of the volleyball is 0.24 kilograms, and we want to find the acceleration. So we know that the net force is equal to mass times acceleration, and acceleration is equal to net force divided by mass. If we rearrange that, we end up with 36 newtons forward divided by 0.24 kilograms. And if we punch this into our calculator, we end up with two significant digits, 1.5 times 10 to the power of 2. And whatever we do to the numbers, we do to the units. So here we have newtons divided by kilograms. So the unit here is newtons per kilogram, and the direction is forward. Now, newtons per kilogram. Let's take a look at this. And a little bit of an aside. Newtons per kilogram. We defined a newton as the amount of force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. So newtons per kilogram, if you expand it, it looks like this. And here we have kilogram divided by kilogram. So we are left with meters per second squared. So another way to write this is 1.5 times 10 to the power of 2 meters per second squared forward. Newtons per kilogram and meters per second squared are equivalent. They're interchangeable, and we often flip back and forth between these two, especially when we're studying Newton's second law, because Newton's second law compares and ties acceleration into force. So being able to switch between the two is actually a very helpful skill. Let's try another example. A 64 kilogram runner starts walking at 3 meters per second east and begins to speed up for 6 seconds, reaching a final velocity of 12 meters per second east. Calculate the net force acting on the runner. So we're given mass, initial velocity, final velocity, and elapsed time, and we want to find net force. We know that net force is equal to mass times acceleration, and we have the mass, but we don't have the acceleration. So we're going to have to find the acceleration, which is something that's common in this section, where they don't give you the acceleration. You have to look back to kinematics and be able to calculate the acceleration, which is delta v over delta t, which is v2 minus v1 over delta t, which is 12 meters per second east minus 3 meters per second east divided by an elapsed time of 6 seconds. If we punch this into our calculator, we end up with an acceleration of 1.5 meters per second squared east. So now I can calculate the net force now that I know the acceleration. I know the mass is it's 6.4. Rather 64. Let me just start over. It's 64 kilograms. And the acceleration we just said was 1.5 meters per second squared. But for this, since I'm finding force, instead of writing it in meters per second squared, I'm going to write it in newtons per kilogram, because I mentioned above that they are equivalent. And you'll see why. When you multiply these together, the kilograms will cancel out and you are left with newtons as your unit. Punch these into your calculator and you end up with a net force of 96 newtons east. Okay. Let's try the next example, sample problem number 3. Here we have a free body diagram showing a 9,100 kilogram jet moving slowly on the ground. It fires its engine, resulting in a force of 22,000 newtons east on the jet. And the force of friction on the jet is 3,800 newtons west. We also have a force of gravity down on the jet and the normal force up on the jet. Now, since the jet is resting on a level surface, then we know that the force of gravity and the normal force will cancel each other out. So the only two forces acting on the object are the force applied by the engines, which is 22,000 newtons to the east, and the force of friction, which is 3,800 newtons west. Now, if you notice, we have expressed the force applied, which is 22,000 newtons east, as plus 22,000 newtons. And we've expressed the force of friction. Instead of writing 38,000 newtons west, we wrote negative 3,800 newtons west. So in this example, the author has used the sign convention. They have let east be positive, therefore west will be negative. This is similar to the sign convention that we used when we were studying projectile motion in section 2.3. In this example, I'm going to use the east and west direction instead of the plus or minus, but following this, I'm going to use the plus or minus sign convention throughout. I just want to set up how to answer Newton's second law questions, this time using the directions instead of the plus or minus, just so that we can strengthen and reinforce that. Okay? We want to find the net force on the object. So the net force on the object is what we need to find. The first step in doing so is to list all forces acting on the object. And we're going to make sure we include direction. So here we have the force applied by the engine plus the force of friction. Now notice I've kept the arrowheads on top and we're adding them together, and we have to make sure we put direction in. So we have 22,000 newtons east plus 3,800 newtons west. These are collinear vectors, but they're not in the same direction. So we're going to have to change them to both the same direction. I'm going to change friction to negative east. When you change the sign, you change the direction. So we have 22,000 newtons east minus 3,800 newtons east. And if you punch this into your calculator, you get 18,200 newtons east. So the net force acting on the engine, or on the jet rather, is 18,200 newtons east. In part B, they want us to find the acceleration of the jet. In order to find the acceleration of the jet, acceleration is equal to net force divided by mass. That's 18,200 newtons east divided by the mass of the jet, which is 9,100 kilograms. If you punch this in, you end up with 2.0 newtons per kilogram east. And you can write, therefore, the acceleration of the jet is 2.0 meters per second squared east. I've changed newtons per kilogram into meters per second squared. If you left it as Newton per kilogram, you would get full marks. It is 100% correct. I just wanted to strengthen and reinforce that both of these are interchangeable. All right, we're going to do a really classic physics problem. And this problem involves a cart. In this case, it's a frictionless cart, which can roll freely on this tabletop or desk. And it's attached to a rope. And the rope is hanging over the table across that pulley. And there's a mass attached to it. So if you could imagine what would happen in this situation, the force of gravity is going to pull this mass down. As a result, it's going to pull this cart to the right. And since it's going to be moving downward, there's going to be an acceleration. If this starts from rest, this mass will accelerate downward and the cart will accelerate to the right. Since they are attached by a rope, the acceleration of this system will be the same. So the acceleration of the mass will be equal to the acceleration of the sliding cart. So we want to study this and determine the acceleration. Let's do a few things first. Let's review what force is causing this whole system to accelerate is the force of gravity. And the force of gravity is equal to mg, where g is the acceleration due to gravity, which we studied back in Unit 1, and we said it's 9.8 meters per second squared, or newtons per kilogram, in the downward direction. As I mentioned, sample problem 1 is frictionless. We will do examples with friction. Let's read the sample problem. It says, in an investigation, students place a 0.80 kilogram cart on a table. They tie one end of a light string to the front of the cart, run the string over a pulley, and then tie the other end to a 0.20 kilogram hanging object. Assume that no friction acts on the object. In part A, they want us to determine the acceleration of the cart. Now, I'm going to use a sign convention, a plus or minus convention to indicate direction. And I want, since this object is going to be accelerating in this direction, to the right for the cart and down for the mass, I'm going to say let right and down be positive. So we know that left and up are negative. You can assign basically any directions to be positive or negative as long as they are collinear. In this example, we're going to make right and down be positive because this is the direction the cart will travel and the mass will travel. So, our first step in answering this question is to draw a free body diagram of each of the objects. And we're going to show all the forces acting on each object. So we'll start by drawing a free body diagram of mass number 1. Your free body diagram doesn't have to be detailed like this one, but I wanted to do that because I just want you to be able, if I drew a square box, I wanted you to be able to distinguish between the cart and the mass. And the mass of this guy here is 0.80 kilograms. I may even go the step further and color it in for you. So there is no question as to which object we're talking about. Okay, now let's list all the forces acting on each object. Let's look at the cart on top of the table. The cart on top of the table is going to move to the right, and it's going to move to the right because the rope is pulling it to the right. So we need to draw the force that the rope exerts on the object. And that force that a rope exerts on the object is called tension. Okay? We'll do the same thing for the hanging mass. Call this M2 and it's 0.20 kilograms. I'm going to color it in just so you know what we're talking about. I'm sure you already do. And we said that the force of gravity is going to pull this object down. And the force of gravity is equal to mg. In this case, it's m2g. Now this object is not just like this. It's not only influenced by the force of gravity. If it were, it would be free falling, but it's not free falling. It's attached to a rope. And that rope exerts a force in the upward direction, and we're going to call it tension. Now, if you notice, I drew this force of tension in red and this force of tension in red. And I did that for a reason. Because both of these objects are attached by the same rope. The force of tension on that rope is uniform. So the force of tension pulling the cart to the right is equal to the force of tension pulling the mass in the upward direction. Okay? And that's a bit of a trick that's going to allow us to solve this. Anytime you do a hanging mass sliding cart question, know that if they're attached by a rope, that the tension will be uniform throughout the rope. Therefore, the tension acting on the cart will equal the tension acting on the mass. Okay, the second step is to list all the forces acting on the object. So we're going to say, and we're going to use plus or minus to indicate direction this time. For object number 1, the net force acting on object number 1 will be plus the force of tension. And I used plus because for this cart on top of the table, tension is pulling it to the right. The second thing I'm going to do is replace the term F net with the equation MA. Just going to make a little room. So in the first step, I listed all the forces on the object. In the second step, I'm going to replace this term here, net force. I'm going to replace it with MA. But to be specific, we're talking about M1A because we're looking at the mass of object number 1. So M1A is equal to the force of tension. All right. We're going to do these same 2 steps, list all the forces, and replace the term F net with the equation for object number 2. So for object number 2, the net force, and remember we're using plus or minus to indicate direction. So we are going to talk about first the force of gravity. Since the force of gravity is down, and we made down to be positive, the force of gravity, we're going to have a plus sign. And next, there's the force of tension. And since the force of tension is pointing up, we made up to be negative, so this is going to be minus force of tension. So for object number 2, the net force is equal to the force of gravity minus the force of tension. And again, I've drawn the force of tension in red for both examples because the force of tension for both of these is the same. Next, I'm going to replace F net with the equation for F net, which is in this case M2A. And I'm also going to replace the force of gravity. Since we know the force of gravity has an equation, I'm going to replace that with plus M2G minus the force of tension. Okay. The whole point of this question was to determine the acceleration of the object. I have acceleration in this equation here, but I also have another unknown, which is tension. In the second equation, I have acceleration, but also another unknown. So I have 2 unknown variables in these 2 equations, and in math, whenever you have 2 unknown variables, you have to remove one of them. And you can use one of 2 methods, the 2 methods that they use in math to solve for an equation with 2 unknowns is the substitution method or the elimination method. So we're going to solve this. Since we know that the force of tension in this question is equal to the force of tension in this question, what we're going to do is rearrange each equation for the force of tension. So in this first example, force of tension is equal to M1A. And in this example, we're going to bring the force of tension over this side, and then we're going to bring M2A over this side. When you do, they will change their signs. So we end up with force of tension equals plus M2G minus M2A. Sorry. M2A. Okay? Now, since I know the force of tension equals M1A, and the force of tension equals M2G, and the force of tension for both of these is the same, so if force of tension equals this, and force of tension equals this, then I can say that M1A must equal M2G minus M2A. I set this equal to this because they both equal the force of tension. All right, so I've eliminated one unknown variable by combining these two together. So we've removed the force of tension, and all we have left, the only unknown variable that we have, is the acceleration. And that's good because that's what they asked us to find. So we have acceleration in a term on the left-hand side of this, and an acceleration in a term on the right-hand side of this. So we have to collect like terms. We're going to bring all the accelerations to one side. So we end up with M1A. And then when we bring that negative M2A over the equal sign, it becomes plus M2A. And it's equal to plus M2G. The next step is to factor out the A. So we are left with A times M1 plus M2 equals plus M2G. And then divide both sides by M1 plus M2. These will cancel out. We are left with acceleration equals plus M2G over M1 plus M2. Folks, every time we do this, we will end up with this example. Every time we do a hanging mass sliding cart question without friction, it's going to look like this when we solve the acceleration. This acceleration equation is basically stating that the net force that is causing this system to accelerate is the force of gravity acting on the hanging mass, and the acceleration will depend on the mass, the total mass of this system. Okay? Let's sub and solve to find the acceleration of this system. So M2 was 0.20 kilograms and G was 9.8 newtons per kilogram. Notice I'm not putting direction in because we put direction up top. We assigned a plus or a minus for the direction. Remember when we did this up here? That's when we indicated direction. If you were to put a direction in at this point, you would actually contradict yourself. You would flip the direction because you put direction in twice. Now divide this by M1, which is 0.8 kilograms, plus 0.20 kilograms. And if you punch it in to your calculator, you should get to two significant digits, positive 2.0 newtons per kilogram. And that tells us acceleration for the cart is 2.0 meters per second squared, right? Because that's what the positive means for the cart. And for the mass, it's 2.0 meters per second squared down. Remember, when you're stating your final answer, it's important to state the actual direction. So we're going to go back. We're going to remember what we said left and right were. And we're going to make sure that we convert it back to the original directions. All right. In part B, they ask us to calculate the magnitude of the tension. Now we actually have two equations for tension that we can use. We rearranged the free body diagram of mass number 1 for tension, and we arranged the free body diagram for mass number 2 for tension. So we actually have two possible equations that we can use to find the tension. I'm going to use equation 1 because it's quite simple. The force of tension equals M1A, where M1 is 0.80 kilograms. I almost put in the wrong mass. That's a very common mistake, is when you mix up M1 and M2. So make sure you're clear. And we're going to put in the acceleration. The acceleration is plus 2.0 newtons per kilogram. I use plus because the acceleration of the cart is to the right. If you punch this into your calculator, you end up with a force of tension acting on the cart of positive 1.6 newtons. Therefore, the tension on the cart is 1.6 newtons, and the direction is right. If you did this for the hanging mass, you would notice that the tension, the direction of the tension on the hanging mass, is in the upward direction because tension is pulling up on the cart. All right, you'll be doing some examples. You'll be doing the hanging mass sliding cart example over again in the homework. And then we're going to also introduce friction in the homework. Stay tuned for a video that shows you how to incorporate friction for these examples. Try the homework problems and do any corresponding LMS quizzes assigned for this section. Good luck.